So a couple things real quick. First of all, let's take a look at the if you haven't been to the website, please make sure you go there. Remember, you can get there by going to iechs.org, clicking on Contact Us, and then clicking on My Name. Here's all the college prep stuff. Let me just pull up the calendar real quick. Let's look at that for a second. And I still have a couple people that haven't turned in their disclosure, so you definitely need to do that. Let's see. So we're right here. Yesterday we went over more calculator stuff, went over questions and all that sort of thing. Today we're going to cover 3.1. We're going to finish it up on Tuesday. Remember, Monday's a holiday, so you don't have to come then. We'll finish up 3.1. We may do a little bit on of the calculator worksheet and stuff like that, so make sure you bring your calculator. Okay? If you happen to be gone, oops, so let me go back here. If you go under the lecture notes, here's chapter 2 and 3, which is what we've been covering. The very first thing here, for each one of the chapters, for each one of these, I'll have a page of video lecture links. So I know we haven't done anything too terribly difficult so far, but if you open those, there are links for everything that we've done so far this week. So we've had 4 days of class. There are 4 videos there. So if you got stuck on something, couldn't remember, what went on, and your notes weren't good enough, you could go back and watch the lecture again. Okay? Questions? Okay. And later today, I'll have the stuff for 3.1 up there also. All right. Let's see. Let's take a look at this guy right here. So this section is about functions, and you dealt with functions in Math 1010. So a function is a very consistent mathematical rule, and what it does is it takes whatever you plug in, it does some math on, and it spits out an answer. Okay, and it does the same thing every single time. So if it's Friday and we take some function and we plug in a 7 and we get out a 2, if we come back on Monday and we use the same function and we plug in a 7, we better get a 2 out. We better not get something different than that. Okay, they're really, really consistent. Okay. And we also use this type of notation. This is called function notation, and we say it this way. We literally say f of x. Okay? So that's called function notation. Okay? And if you, for those of you that took 1010 here, you saw that type of notation. All right? So just like we normally, you've been used to working with things like this, like y equals 2x minus 4. You're really familiar with working with x's and y's. Y is the same as f of x. Okay, so y is exactly the same as f of x. Now, function notation has a lot of really nice properties, and we're going to try and develop some of those. So here's our function right here. This is the first one. Okay, or at least it says, is this a function? F of x equals x minus 3. So here's what we do. Instead of writing an xy table, we're going to write an x f of x table. So we're going to plug in a -2 and we're going to see what comes out. So f of -2 is going to be, now notice what changes here. Where there used to be an x, I put a -2. So wherever there's an x, I put a -2. So this would be -2 minus 3. So this would be -5. And there's the ordered pair that we'd graph. Okay. If I plug in a -1, wherever there's an x, I put a -1, so a -1 here. So what this function does is it takes whatever we plug in and it subtracts 3 from it. So this is going to be -4. What's f of 0 going to be? F of 0? -3. What's f of 3 going to be? F of 3, because we take whatever, this function takes whatever we plug in, it subtracts 3 from it, so this is going to be 0. Okay? The next one's a little more complicated. What is f of a going to be? Yeah, it's going to be a minus 3. Okay? Whatever we plug in, sometimes that's called the argument, whatever we plug in there, all this function does is it subtracts 3 from it. So this one happens to be an expression, it would just be a minus 3. So whatever we dump in, sometimes it's helpful to think of a function like a machine. You dump something in and it spits out whatever the answer is. Okay, so in this particular case, what this machine does, what this function does, is it just subtracts 3. So no matter what you plug in here, whether it's a 5, it'll subtract 3. A 10, it'll subtract 3. If it's a negative 423, it's still going to subtract 3. Okay? Now let me write something really silly. What if we dumped in a school bus? What would this function do to the school bus? Yeah, what would come out would be a bus minus 3. Now that doesn't make any sense, okay? Because we wouldn't dump a school bus in there. Okay, but the idea is important. Okay? The function does the same thing every single time. All right? So let's talk some vocabulary here. The things that we dump in, those are called the domain, and the things that come out, those are called the range. And we can describe a function this way. We can say each member of the domain corresponds with exactly one member of the range. Okay, now that's really wordy. That's a long sentence and everything. Okay, domain and range, those are kind of weird words. Okay, but we could say it this way. Each x corresponds with only one y. That's that consistent part. Every time we dump the same number in, we're going to get that same number out. Like when we dump in a 7, we're going to get out a 2 or whatever it happens to be. Okay, so functions don't always have to deal with numbers though. All right. So let's say we were doing birthplaces of all the students in Math 1010 or college prep or whatever it happens to be. Okay? So let's take Alex here. Is that okay, Alex? Okay. And let's take Caitlin. And we'll take Chase. And let's see, we'll do Amanda. And let's see, Josh. Those people can all be in the domain because they're in this class. Okay, now Alex, where were you born? Okay, Alex was born in Salt Lake City. Caitlin, where were you born? Logan. Chase. Salt Lake City. Now, do I need to write Salt Lake City again? I don't. Once it's in this set, once it's in that group, I don't need to write it again. Amanda, where were you born? Wow. Okay. And Josh, where were you born? Okay. Okay, so these are all in the domain because they're people in the class. These are all the range because they're birthplaces. Okay? So we can do what's called a mapping. We can say, well, Alex corresponds to Salt Lake City. Caitlin corresponds to Logan. What does Chase correspond to? Salt Lake City. So I'm going to draw a line right here. And some people may, well, that doesn't quite look right, but we'll go with it. Okay, Amanda, Liberty, Missouri, and Josh, Pasadena, California. Okay, now my question for you is this a function? Does each member of the domain correspond with exactly one member of the range? Yeah, okay. There's no problem with Chase and Alex being born in the same place. Okay, this would be a huge problem. What if we had Josh in Logan also? Would that be a function? Okay, so for 2 reasons. One, this thing in the domain corresponds to 2 places, and why wouldn't that make any sense in real life? You can't be born in 2 places. Okay, so that one, okay, this is a function. If we added that other line, it wouldn't be a function. Okay, so let's talk in terms of numbers. So each one of the first elements, okay, each one of the x's, okay, that's part of the domain. So we're going to put a -4 there. Let me change back here. A -4, a 0, a 1, a 2, and a 3. Those are all elements of the domain. And the range, those are going to be the y's. So that's going to be, let's see, a 3, a 4, a -1, a 1, and this last one is also a 3. I don't need to write it again, do I? Okay, so let's map these. Let's show the correspondence. Okay, so 4 corresponds to 3, 0 corresponds to 4, 1 corresponds to -1, 2 corresponds to 1, and 3 corresponds to 3. Okay, is that a function? Yes. Okay. Now, we already wrote these. We kind of already answered what the domain and range is. We like to put those in, so let me make this look a little bit better. This is as nice as I'll make a set bracket. Okay. Kind of looks like this. That's a set bracket. So the domain would be the set of -4, 0, 1, 2, and 3. Okay. That's as good as I make them. Now I just make them look like squigglies. The range, that's going to be 3, 4, -1, and 1. Okay? Now I'm going to change to red again, and let's add this guy right here. What if we added 1, 3 to that setup there? What would be the problem now? Okay, 1 would correspond to 2 different things. So the problem is right here. The 1 corresponds to 3 and it corresponds to -1. And that's not okay, right? So the answer there is nope, it wouldn't be. Okay? I should clean these notes up, shouldn't I? I could just add that. All right, everybody good there? Okay. All right. Okay, I'm going to leave this so you can see both of them. There's a good reason why we can't have an x corresponding to 2 different y's. So we pointed out, let's see, let's go ahead and graph these points here. So -4, 3 would be right here. 0, -4 would be right here. 1, 1 would be right here. 2, 1 would be right here. 3, 3 would be about there. And then we said this was the problem, right? Adding that one would make an issue. Okay, so let's put that one on here. 1, 3 is right here. Okay, so here's the problem. This point and this point have the same x-coordinate but different y-coordinates. And what that means is they're both on the same vertical line. So you can tell by looking at a graph whether or not it came from a function because it has to pass what test? The vertical line test. Okay? And you want to make sure you spell vertical right. It's not C-L-E, it's C-A-L, vertical. Okay? Okay. So let's draw a graph that is a function, any one you want. All you have to make sure is that it passes the vertical line test. It can't like cross back over itself. Okay? So would something in the shape of like a parabola, would that work? Yep. Would a line work? Yep. Would something that squiggles around like this work? Okay. Some of you may have seen some trigonometry, maybe something that looks like this. Would that be okay? Anything like that would be a function. Okay. What about a really steep line like this? Is that okay? Still okay. Okay. How do we draw something that's not a function over here? Same x-coordinate for 2 points. So if I did something like this and made the graph go through there, that wouldn't pass the vertical line test. That wouldn't be okay. So anything that does kind of goes back on itself like that, that would not be a function. Good there? What about this? What about a line that's straight up and down? Nope, not a function. Okay? Okay. So a good example would be anything that looks like that. Okay? All right. Any questions? You've all seen that stuff before, right? Okay, just a good reminder. Okay, let's take a look at example 4. It says given g of x equals 5x minus 1, and we typically label our functions different letters. So we used f before, now we're going to call it g and stuff like that. Sometimes you'll see an entire section where they'll all just be called f. Okay, so they're all just new functions. So wherever there's an x, what are we going to plug in? We're going to put in a 4. Okay, and everybody watch, please. This is a little bit of a silly thing to do on this particular problem. Because if we're supposed to plug in a 4, and we know that, and we're going to take it and multiply it by 5, well, 5 times 4 isn't that difficult, and then we're going to subtract 1. So the answer to this is 19. So G of 4 is 19. So 4 corresponds to 19. Now you could probably do that in your head, but it's really valuable to think whenever I plug something in, I should at the very least visualize that I've plugged that in parentheses. Okay? So if you don't want to write this one this way, 5 times negative 3 in parentheses minus 1, at least think of it that way, visualize it that way in your mind, and then think, well, that's going to be negative 15 minus 1. So G of negative 3 is negative 16. Okay? At least think of it that way. Because then when we get to stuff like this, it makes it even easier. So if the rule is G of x equals 5x minus 1, and now I want to know what G of a is, what am I plugging in for x? Just an a, like we did on the front side. So this is going to be 5 times a minus 1. Now, that's a little bit more confusing. Okay, if you brought some pre-algebra student in here or somebody that was in 6th or 7th grade, they'd look at that and go, that can't be an answer. It's not a plain old number. Well, this is the answer. Okay? The answer to this is just that expression. All it said to do was plug in a. We plugged in a. We got 5 times whatever a is minus 1. And then they get a little more difficult. What if we wanted to find G of a plus 1? And this is where it's helpful to at least to visualize, even when we're plugging in numbers, that we plug them in parentheses. So this is going to be 5 times something minus 1. What is that something that we're plugging in? A plus 1. Now, would we leave it like that? Nope. Okay, we've got some work to do. But what I want you to notice is this. Wherever there used to be an x, there's now an a plus 1. So there used to be an x here. There's now an a plus 1 here. We're just going to do a little bit of simplifying. So this is going to be 5a plus 5 minus 1. So G of a plus 1 is 5a plus 4. That would be our answer. And you've got some problems like that. Would you do E, please, and check with your neighbor? See if you can do E. What's G of A? Didn't we figure out what G of A was up here? So we're going to take G of A, which is 5a minus 1, and then we're going to add 3 to it. So what is the answer to this problem? 5a plus 2. Okay. Would you do F? F is find G of x plus h. G of x plus h. Let's talk about this in words. G is take whatever you're plugging in for x, multiply it by 5, and then subtract 1. So if we're going to plug in x plus h, it's 5 times whatever you're plugging in, which is x plus h, and then we're going to subtract 1. So we'd write 5x plus 5h minus 1, and that would be it. That's weird, but that's the answer. It's just an expression. Any questions? All right. There are 3 typical functions that have domain issues. Anybody remember what they are? If you were in my 10-10 class, I'd be really disappointed if you can't name all 3 of them. Okay, you're breaking my heart right now. What? No problem with exponentials. Yeah. Okay, you can't take the square root of a negative. Okay, you can't take an even root of a negative. That is not allowed. Can't take an even root of a negative. So you can't take the square root of a negative, the 4th root of a negative, the 6th root of a negative, and so forth. Okay, what's another one? Very good. Can't divide by 0. You can't take any number and divide by 0. Okay, so that is not allowed. Can't divide by 0. No even roots of negatives. You can't divide by 0. And then there's one more that we covered at the end of 1010. Shane? Okay. You can't take the log of a negative or 0. That's not allowed. Oops. Let me do that in red. Okay? Can't take the log of a negative or 0. Now, we don't run into those all the time. Okay? Logarithms you encountered at the end of 1010, you may have seen them if you took Algebra 2 already or something like that. Okay? But those are the three functions that typically give us problems. They're not the only three, but they're the three most common. You're going to run into some more if you end up taking trigonometry and stuff like that. Okay? So if you ever have an even root, you got to be careful. If you ever have division, you've got to be careful. And if you ever have a logarithm, you've got to be careful. You can't divide by 0. You can't take an even root of a negative. Okay, so we've eliminated 0 and we've eliminated the negatives on some problems. And on logarithms, it's both. You can't do a negative or a 0. Okay? So let's take a look at these problems right here. And it says, find the domain of the following functions. So let's look at this function right here. Okay, when we say domain issues, what that means is you're going to have a problem with some numbers that you plug in. You can't plug in anything you want. So, of these three issues here, which one do we have going on in this function? We've got division, right? So we've got to be careful. We can't divide by 0. What would make this equal to 0? 6. So we say x cannot equal 6. Okay, that would be the domain. Now, you can write it like this, or you could write it like this. You could say from negative infinity to infinity. You could say you can plug in anything you want. So let me do this. The domain is from negative infinity to infinity as long as it's not equal to 6. Okay? Or you can just say this guy right here. That would be okay. Any questions? Okay, let's take a look at the next one. We've got division in this problem. We don't have any even roots and we don't have any logarithms. The one thing we have to be careful of is we can't divide by 0. So what number can we not plug into this? Okay, so we'd say x is not equal to 3. That would be our domain. You can plug in anything you want. Pick any number. As long as it's not 3, you're going to get an answer. Tatum, give me any number you want. 5. So if I take 5, I put a 5 on the top, and I do 5 minus 3 here, I get 5 over 2. I get an answer. Okay? You could do that with any number, fraction, decimal, anything you want except for 3. Because if I pick a 3, watch what happens. I get a 3 over 3 minus 3, and then I've got 3 over 0, and just like we saw up above, you can't do that. That's the only number where it doesn't work. Okay? How about C? How about this guy right here? Does it have any even roots? Nope. Any division? Nope. Any logarithms? Nope. Okay, if you picked a number, okay, there are 25 people in this room right now. If we each picked a different number, go ahead, pick a number, get it in your head. If you plug that in, what's the first thing you do with it? First thing you do is you square it. Then what do you do? Subtract 10. Anybody not get an answer for that? Any number you plug in, you can square any number you want. You can even square 0, can't you? 0 squared is 0. Minus 10 would be negative 10. So h of 0 would be negative 10. We don't have an issue with that. Okay? Any positive number is okay to square. Any negative number is okay to square. So no issues whatsoever, yeah. Okay? So here's what Samantha's doing. Samantha's thinking, wait a minute, he might be telling us something that's not quite true. So she's thinking, what about something like this? What about a number like the square root of 10? If I take this and I plug it in there, this would be the square root of 10 squared minus 10. Square root of 10 squared is 10. 10 minus 10 is 0. Did it give us an answer? Yeah. Is it okay to plug in square root of 10? Yep. Even the negative of that would work out, okay? It produces a cool number. It produces a special number like 0, but it's still okay to plug in. You can plug in anything you want, okay? All right. So how would I write the domain for that particular one? Okay, I can write all reals. I can do that kind of script R that looks something like this. I'm making it look like a B, aren't I? Okay. Or I can say it's from negative infinity to infinity. Okay. Any one of those would be fine. I like interval notation, so I would get used to that. If you don't like interval notation, please adjust. Most of the math books that you'll see, and if you go on to any higher math classes, most of the time they like to see interval notation. Any questions? What's this one got going on? What's example D got going on? Okay, it's got square roots. Okay, so we got to be careful. We can't have this be a negative. Whatever 6 minus x is, it better not be negative, because you can't take an even root of a negative. What else do we have going on here? Okay, we've got division, right? So we can't let it equal 0 either. So whatever this is, it's got to be greater than 0. Pretty easy to solve, isn't it? Can't I just add x to both sides? So I get x, let's see, I'll write it this way. 6 greater than x. Or you might want to write it x, less than 6. Is that all right? Yeah, I said I like interval notation. How would you write that in interval notation? X's that are less than 6. Yeah. Let me do this. Here's 6. That's okay. Here's 6. Let's circle that. Would I shade it in? No. And then which way do I shade? Left or right? Left. It's over here. Okay, so where do the answers start? Way down at negative infinity. You can go as far down there as you want, and it's perfectly okay. And where do they stop? They stop at 6. Okay, now it's always a round bracket around infinity. What is it around 6? It's going to be around here also. Okay, now here's the problem. Some people might say, well, 6 is okay because you can take the square root of 0. Watch what happens when we plug in a 6. If I plug in a 6, that's going to be 6 minus 6. That's 0. Square root of 0 is 0, so this would be 7 over 0. And is that okay? That's the part that's not okay. All right? So that's a little more involved. Okay, next one I think is an interesting problem. This will come up over and over and over again. If you didn't get this figured out in 1010 and didn't get this memorized, I would take the time to memorize it now. What would make the denominator there equal to 0? 3 would, right? Because if you plug in a 3, you get 3 squared is 9. 9 minus 9 is 0, Alex. And negative 3. Here's why. Everybody watch. This is the part I wanted you to keep straight and have memorized. This is a difference of squares. That factors to x minus 3 and x plus 3. So just like up above where we could look at this and say, hey, you can't plug in a 6. Hey, you can't plug in a 3. Now we can look at this one and we can say, well, the one I can't plug in from here is a 3. What's the one I can't plug in from here? Negative 3. Okay? So it would be every real number except for 3 and negative 3. And we used, again, a difference of squares in order to get that. Okay? Okay, take a look at F. Think about F for just a second. And then talk about it with your neighbor and see if you agree as to what the domain would be. Okay? Seriously, talk to your neighbor. We want to know what numbers are okay to plug in. What is the domain? That's what we want to know. Sometimes it's easier to figure out what we can't plug in. This is all reals except for those 2 numbers. Very similar setup. E and F are very similar. The operation that gives us an issue is division. Can't divide by 0. We found some numbers that would produce a 0 in the denominator. Okay? What's the domain here? Anybody want to volunteer a guess? John?
It can't be -3.
Okay, John says it can't be -3. Anybody disagree? Amanda? Amanda says it's all real numbers. Amanda says everything is okay. How many people agree with Amanda? Okay, looks like more than half the class. You are correct. You can plug in anything you want. Okay? Because here's the problem. The only thing that can't happen here is I can't divide by 0, right? Well, is this ever going to equal 0? Does x squared plus 9 ever equal 0? Never. Okay? Now, there are a couple ways that you can arrive at that. You could look at this and say, well, wait a minute. Any number I plug in is going to give me a positive. So if I take something that's positive and add 9 to it, that's still going to be positive, right? Or at the smallest, if I plugged in a 0, I'd get 0 plus 9, which is still positive. Does that make sense? The other thing I could do is, if you remember this from 1010, let's move this to the other side and have x squared equals -9. How would I get the x by itself? Square root, right? So this would be x equals plus or minus, let's see, radical -9. Square root of a negative has an I in it, so this would be 3i. Is that a real number? No. Okay? So any real number you choose would be totally fine. So this one is, let me write it here. The domain is from -infinity to infinity. It's all real numbers. Okay? Any questions? Okay, raise your hand if this is all easy so far. Good. Excellent. Okay, let's take a look at the next little bit, and then we'll flip it over and do a couple more problems. All right. What we want to do is we want to be able to look at this and figure out whether or not it's a function. Okay, so just because we've got an equation doesn't mean we always have a function. Sometimes that's not the case. So what we want to do here is we want to think about this. If I plug in a number, do I just get one answer? So if I plug in a 2, what do I get out? I get an 8. If I plug in a 2 again, do I get 2 answers or a different answer the next time I plug it in? No. Okay. So this is a function. Let's plug in a number. Make them fairly small. That's kind of nice. Let's say we plug in a 2. So if I plug in a 2, this is going to be 4 plus 2 squared equals y squared. So this is going to be y squared equals 8. And then if I want to know what y is, what do I have to do? Take the square root. So this would be y equals, now if I put a square root in a problem, what else do I have to put in there? Plus or minus. Very good, Tatum. So this would be plus or minus the square root of 8. Now I don't even need to go through this step. Simplify the radical. Listen carefully. We put in 1x, okay? We put in a 2, and what we got out was a plus 2 radical 2, and we got out a negative 2, radical 2. So here's 1x that corresponds to how many different y's? 2 of them. Is that okay? As far as the function goes? Well, let's check. Didn't you, I mean, everybody, I think even heard most people whispering, well, guys, it's got to pass the vertical line test, right? Let's graph the 2 of these. Here is 1, 2, and this is a little less than 3. I'd go up 1, 2, about right there. That's this point right here. And then this point right here would be over 2 and down 2 radical 3, about right there. They're on the same vertical line. So is this a function? Nope. Not a function. How about C? You plug in a number, you only get one answer out. If I plug in a 1, I get a 2. If I plug in a 2, I get 2 over 4, so I'd get a half. So pick any number you want. You're only going to get one answer out. So this one is a function. Okay. So some of these require a little bit of thought. Any questions? Sure? Okay, ready to turn the page? And now we're going to look at a graph. Okay, so I'd like you to read that sentence at the top there, a couple of sentences there, and think about that for just a second. Then we're going to look at the next example. It's very similar to what you see in 1050. Might look really weird, some of the expressions in that next example. Okay, but if we kind of try and keep things straight in terms of x's and y's and stuff like that, we should be in business. Okay, so it says, remember that f of x is read f of x. Okay, so that's how we say it. And it literally means what is the function value at x. So if we say f of 2, and f of x is this function right here, we are literally asking ourselves this question. What is the function's value at x equals 2? Or in other words, what is the y value at x equals 2? What y comes out when we plug in an x of 2? So if on this problem I say what is f of 2, I replace every x with a 2, so this is going to be 2 squared plus 1. So f of 2 is equal to 5. Okay, now this is one of the cool things about function notation. When you look at this, if we say f of 2 is 5, the nice thing about function notation is you can look at it and you can tell what the x is and you can tell what the y is. Remember earlier I said f of x is the same as y. So this point right here is the point. What's the x coordinate? 2. Because remember, x is what we plug in. F of x is what comes out. The function value or the y value is what comes out. So this point right here, you can look at it and you can say, well, gosh, we plugged in a 2, we got out a 5. So the x is a 2, the y is a 5. Does that make sense? Because this is a really ugly function. And take a look at this one right here. This is a really weird expression. 3 pi halves. If you've had trigonometry and know that radian measure, then you're in good shape. But if not, just think every one of these is an f of x. So that's an x, and that's an x. Those are each x coordinates. So over here, I'm going to write f of 0 equals, I'm going to write f of 3 pi halves equals, and I'm going to write f of 3 pi equals. Okay? So if this is f of 0, which variable are they giving us? Are they giving us the x or the y? They're giving us the x, and they're asking us for the y. Does that make sense? Just like up here. They gave us the 2. We're plugging in a 2, and we got out a 5. 2 is the x, 5 is the y. So the x is 0. So let's come over here on the graph. Everybody knows where 0 is. What is the function's value at 0? Well, the function is up here, right? It's right there. Or there's the x, there's the y. Or another way to say that is the f of x. So what is the function's value at 0? It is 4, right? Everybody good with that? See the point 0, 4? See the point 0, 4? Just like we pointed out up here. You can look at it in function notation here, and you can see what the point is. So, f of 3 pi halves. Now, 3 pi halves is a really weird thing, but it's still which coordinate, the x or the y? The x. So let's come over here and let's look through these. Can you find a point that starts with an x coordinate of 3 pi halves? Right here, isn't it? Isn't that it? So what is f of, what is the y coordinate, what is the function value when x is 3 pi halves? It's going to be 0. Okay, this one is 3 pi. Which coordinate is that? That's the x coordinate. They're asking for the y coordinate. So they gave us the x coordinate. We need the y coordinate. So we look through here. Well, 3 pi is here. Here's the function down here. So what is the answer to this part? The answer is -4. Oops. Those are the 3 answers to part A. Any questions? Okay. Then it says, what is the domain of f? So if we're looking at the graph, you don't even have to know what function made this graph. If we're looking at the graph and we want to figure out what the domain is, I call this the squish technique. If you want the domain, domains are x's, so we're going to take this graph and we're going to squish it onto the x-axis. So all of these points are going to come down here. All of those are going to come up here. So we basically take the graph and just squish it onto the x-axis. So what part of the x-axis is covered? Where do we start getting answers? Okay, we start at 0, and where do we stop? 4 pi. Round or square brackets? You hear a little bit of both. Somebody want to give me an argument? John?
It's square because it's a finite.
Because it's got a closed endpoint. Okay, this point would actually come down here, and it would touch at 4 pi. So these are square brackets. Okay. Okay, now, if you find the domain by squishing it onto the x-axis, how do you think you find the range? Squish it onto the y-axis. So let's take this graph. Let's push all the points over onto the y-axis. These points would come over here. These points would come over here. And then if we start way down here, where do we start getting answers? Okay, we start at -4, and where do we stop? +4. Round or square? Square. All right. We'll finish this problem, then we'll be done. Okay, then it says list the intercepts. Okay, now remember what intercepts are? Intercepts are anywhere where the graph crosses the x or the y-axis. It can only cross the y-axis once. How many times can it cross the x-axis? Whole bunch, okay? Depends on the function, okay? So list the intercepts. So does this cross the y-axis? Okay, where? Okay, so at 0, 4, there's the y-intercept. What about x-intercepts? What do all the x-intercepts have in common? Y is 0, okay? So the first one is, this would be pi halves, comma 0. What's the next one? Very good. 3 pi halves, comma 0. The next one is 5 pi halves, comma 0. And is there another one? 7 pi halves, comma 0. Okay? You think about the next one. How often does the line y equals 2 intersect the graph? Okay. Or in other words, how many times does the line y equals 2 intersect the graph? So, y equals 2. Horizontal line or vertical line? Horizontal. Remember, y equals the number is horizontal, x equals the number is vertical. So that line looks something like this. How many times does it cross? 1, 2, 3, 4. So the answer to this one is just 4. Okay, F is a great question. Okay, can I erase a lot of these notes here? Okay, look at F. For what values of x does f of x equal -4? Okay, now up above I made a big point of saying f of x is the same as y. So they're giving you the y coordinate and they want to know what the x coordinate is. So this is backwards of what we did up above. It's backwards of part A. We're saying the y-coordinate is -4. You tell me the x-coordinate. Okay? Do we have any places on here where the y-coordinate is -4? Yep, right here and right here, right? In fact, it's kind of like the problem that we did just a second ago where we said, how many times does it cross the line y equals 2? This is basically a fancy way of saying, where does this cross the line y equal -4? Okay, and that is pi and 3 pi. So there's the answer for that one. Okay, and the last one, for what values of x is f of x greater than 0? Can anybody think of another way to describe what that's asking for? Yes? Yep. Where is y greater than 0? And on a graph, how do we know if y is greater than 0? Greater than 0 means it's positive, right, Shane? It's got to be positive. So this is another way of saying, where is the function above the x-axis? And that's here, and here, and here. So that would be from 0 to pi halves. Then we'd start again at 3 pi halves and go to where? Right there, 5 pi halves. And then the last place it's above is 7 pi halves to, we stop at 4 pi. Okay? That's how we'd write that. Okay, think about that. I would look through the assignment. If you look on the back page, that's where your assignment is. On Tuesday, we're going to go over it. So I would get started on the assignment, but you don't have to finish it. Okay, just get started on it, get those ideas in your head. Have a great weekend. Have a nice day off on Monday. You don't need to turn in today's assignment, but if you do have a disclosure, I do need that, okay? Yeah. Turn what in?